Okay, I don't know how this is gonna go. So, this is the first of a new book. I got this book, Theory of Computation. Now, I've actually worked through this book. Um, Maybe not the full book, but maybe to some level the first 5 chapters. Um, I got the PDF up here, so it's a little easier to see. But we're gonna get into it. Mostly I want to just do exercises. I think that's the best. But maybe I should just go over this at a high level. I just read the first chapter, so we're just gonna go through this really quickly. So first off, the book goes through 3 things. It goes through models of computation. It goes over computability theory. You know, what are the limits of computation, and then complexity theory, which is what are the limits of things that can be computed efficiently, or in a reasonable amount of time. So the book starts off with this motivation of like there are what does it mean to be a computer? That's the first question. Is what is a computer? And then it starts off simple with simple models of computation, and it starts off with a finite automata. Um, so then it goes through this example of this door that opens. Honestly, I don't really like this door, but the state diagram is somewhat fine. But then from there it goes on to the formal from there it goes on to a picture of what a finite automaton looks like. So finite automaton is basically a model of computation which the amount of memory you have is extremely limited. And it's limited in that sense by the number of states you have. If you need to remember an infinite number of things, then you won't be able to, or an unbounded number of things, maybe a better way of saying that, then um, then a finite automaton is not going to work. But anyways, so this is a finite automaton, and basically what it does is it processes input strings. So, um, and what it really does or returns is a yes no. Okay, so any dot or state with 2 circles is, dude, there are these small flies, and the small flies always go for your eyes, and I think it's because there's moisture in your eyes. I remember looking that up, but it's so weird and it's so annoying. Some bugs are chill, other bugs are just annoying. Why are you going for my eyes? Now, I can't kill bugs, that's not part of my life, but damn, that's annoying. Um, okay, so this is the state diagram. That's the definition. And they just never leave you alone. Okay, so you give it an input string and you sort of follow these arrows based on what the next letter of the input is. And if you end on a double circle, then you accept. And it's part of what they call the language of the finite automaton. The language is defined as just every string that accepts. And oftentimes there's a concise way to describe the language. You know, all strings composed of 0 and 1s that end in a 1. That is a language. Okay, here's the formal definition. We'll just jump to this because if you have any math experience, it's actually easier than understanding anything else. So you have a finite set of the states, you have a finite set of the alphabets, which are the labeled arrows, and then here you have basically you take a pair and you return a state. You take a pair of the states and the letters or the alphabet, and you go to a state. So this is the transition function. And then finally you have a start state, single start state, and then you have a subset of the states which are accept states. All right, so that's a pretty nice definition, I think. Let's see. Here's an example. And a good thing to do is to try to figure out a concise way of explaining what the actual thing does. So it needs at least, okay, so it can be any number of zeros. This is a really weird one. They describe it as something different, as that contains at least one and an even number of zeros follow the last one. But that's not actually true because there's a 1 here. I think that's a mistake. Oh, wait, that's actually, no, that's actually correct. Because if you have a last 1 here, yeah. Because that would be the last one. So anyways, just an example. It's a nice example. This is going to be an extremely nice way of describing the transition function as a table with the alphabet on the top and the states on the side. This is going to be used all the time. L of some machine is equal to M. And then the terminology, we say that a machine recognizes a language. Okay. Here's some more examples. This is an easy one. You should be able to figure this out. This ends, basically you can see that the only arrows going to it, to the accept state of this machine, are 1s. So then you know that this machine must end in a 1. Or every string in the language must end in a 1. So and it turns out it's any string that ends in a 1. There you go. Thus the language of M2, this machine, is some W, some string W, such that W ends in a 1. All right, this one's interesting. Looks like it ends in 0 or it's empty. It's empty because it's the start state. All right, so that's an easy example. This example is cool. It might look complicated, but let's just take it from the left, and then we'll do the right. So the left, if you get an A, then you accept. So that's chill. But now if you go to a B, and you keep doing A's, then you're still in Q1. You're still in an accept. If you get a B, though, then you reject. But if you get another A, then you accept. So basically, this is going to be like, it's going to be like the composition of M2 and M3, because in this case, it accepts if it ends in an A. And this one accepts if it ends in a B. And so what this machine is doing is that it will accept if it ends with the same symbol that it started with. So that's a cool example, because this sort of shows that you can compose these things to get more complicated behavior. This is this modular arithmetic one. So basically you can see here you have 2 states. You got 3 states. You got a 0, you got a 1 and a 2. And now the alphabet is actually 4 states. So if I start at 0 and I go to 1, then I go to 1. If I do another one, I go to 2. And if I go to another one, I go to 3, which is 0. And so this is this modular arithmetic thing with the additional capability that you have a reset symbol. So, and it accepts if the final tally is 0 mod 3, keeping the resets into account. So that's a good example. So just make sure I'm going through the thing. Yeah, good example. Oh, here, this is cool. Wait. This example is nice because it's a generalization of the modulo example, but it shows that first that you might not be able to draw it, but also that as, let's say in this case, the n for mod n changes, you need to actually add more you need to add more states. So the state count could get big kind of quickly. And we'll see that the state count gets really big pretty fast. Okay, the formal definition of computation is really not that complicated. So we have, basically, it says, all right, so this is the formal way that a DFA, a deterministic finite automaton, computes. So let's say we have some string, and we break it down into its component characters. M is said to accept the string if there's a sequence of states that follow this thing. So we start at the start state, then the transition function, we basically, it follows the definition of the transition function. And then finally, the last state is an element of the accept states. Yeah, so here we go. Condition 1 says the machine starts in the start state. Condition 2 says the machine goes from state to state according to the transition function. And condition 3 says the machine accepts its input if it ends in an accept state. They say M recognizes language A if A is equal to the set of strings that okay, this is an important definition. So a regular language is defined as some language that is recognized by a finite automaton. All right, that's just a little example. Okay, this thing about designing a finite automaton, I didn't really need this. I thought this was kind of long-winded. But it's just trying to get you into the mindset of like what might certain like if someone hands you a description of a language, how might you construct a DFA for it? And it does this even odd example is good. And I actually, when I was working through the book, came back to this even odd example all the time because it was a good like test model to like test strings on, test properties on, stuff like that. All right. Another example of how to design them. Okay, this is important. Okay, so now that we've sort of gotten a handle and seen a few examples of DFAs, what we want to know, and the formal definition, we want to know how do we compose DFAs into bigger and bigger things? What that means is we want operations where we can take two languages, and in this case, regular languages, and we want to combine them together in certain ways and still have them be regular. That's the definition of a closed operation. And these have a special name. These are called the regular operations. Basically, given two languages, they're union. So X is in A or X is in B. That's the first regular language or regular operation. Concatenation. This is where we basically have two languages, and the concatenation language is all X before Y, such that X is in A and Y is in B. And then finally, A star is basically it's almost like a power. It's like if you have some language A, then A star is as many copies of elements of A as you'd like. So, this definition. You have some x1 to xk. K is greater than or equal to 0. Notice that K could be 0, so that means that the empty string is always an element of A star. Oh yeah, here, they say that. The empty string epsilon is always a member of A star, no matter what A is. All right, this is actually a good example because it takes like 1 second to understand. So let's say our language is just the words good and bad, and then our second language is boy and girl. The union is just good, bad, boy, girl. Now the concatenation is good boy, good girl, bad boy, bad girl. And then A star, you can see here we get good, bad, good, 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 bad, bad, good, bad, bad. It's so on. So it's going to be I mean, we're going to get into this hopefully, but as soon as possible. But it's going to be important to show that even though we're calling these the regular operations, we don't yet have proof that they're closed operations, meaning the union of two regular languages is regular. We haven't proven that yet. So this is what Theorem 125 is. And this is actually really cool. This is one of my favorite proofs from this book. So say someone hands you A1 and A2 that are both regular. We now need to prove that A1 union A2 is regular. The way we're going to do that is we're going to construct some DFA that is exactly equal to this language. So we get A1 and A2, and we want to show that A1 union A2 is regular. Yeah, so imagine that you could, right, that this is probably the best place to start with this proof. Imagine, so you have these two languages, and you know they're regular, so you know that there's some DFA for each of them that recognizes that language. Now you have your input string, and basically what you want to do is you want to run that input string on both of them at the same time. And if either of them end in an accept state, then you want to accept. So that's conceptually what you need to do, but just saying that isn't enough because, first off, how do you run them both at the same time? Particularly, how do you run them? Maybe you could just say run them both at the same time, but that doesn't mean it's regular. You need to run them in the same time in a way that the way you run it is a finite automaton. Okay, so we're going to construct a finite automaton that does this simulation in parallel. Okay, so anyways, the punchline is what you're going to do is you're going to construct a DFA where the states of your new DFA is the Cartesian product of the two original ones. And the way that works, because now you have K1 times K2 total number of states in your new machine. That'll allow you to keep track of, at which place both of them are in. And then all you need to do is that on the you need to update your transition function so that you're given this pair. You now need to compute the original transition function for the first part of the pair and the second original transition function for the second part of the pair. And then you just make that a pair. So we're going to see that syntactically right here. Okay, so our new M is going to have states of the Cartesian product of the original sets of states. So we have M1 recognize A1. And then, so Q1, sigma, and we assume that the alphabet is the same in both, but it really doesn't matter. You could have, here, they say here, we would then just modify the proof that if they were different, the new alphabet would just be the union of the two alphabets. So it's kind of a detail that's not important. Okay, so then delta 1, we're going to be the transition function of M1. Q1 is the start state of M1, and F1 is the accept states of M1. Similarly, Q2, delta 2, little q2, and F2. Anyways, let's get on with it. Alphabet, that's all good. Now, here's the cool part. The transition function, you basically just map delta 1 onto the first part of the pair and delta 2 onto the second part of the pair, and then you make that a pair. And this gives you a way to keep track of, to basically make a transition function that calls two transition functions. And this is perfectly well defined. I mean, yeah, there's really no issue with doing that because you're just stitching together this table. Oh, and then Q0 is the start state, and you just let that be the start states of the original models. So that's all chill. I'm really just trying to rush through this to get to the exercises because the exercises are the fun part, man. Oh, this is important. This is really cool. Okay, so for the accept states, remember, if we want the union, then we want if either M1 or M2 ends in an accept state, then we accept. So this is going to be or. Now, if we had and, that would be this. Because it's the Cartesian product of the accept states of the first machine and the accept states of the second machine. So this would be the intersection, and they say that here. And there's a really cool part of this footnote that says M would accept the string if only if M1 and M2 accept it. So the resulting language would be the intersection, not the union. In fact, this result proves that the class of regular languages is closed under intersection. So this proof, we kind of got a double whammy out of it because it's like you get intersection and union are closed for regular languages. All right, so now this is where things really take a turn in this book because you're like, great, we just did the first one, we just got to bang out the next two, and now we like have all our three operations closed and we can use them all we want. We could take two DFAs, take their union, who cares, do whatever we want. But doesn't really work out that way. So we're going to try concatenation. And there is, let's see if we can, I don't know if I could possibly say it better than the man who wrote the book, but we just want to go to, it's the end of the first lecture. These lectures are just definitely going to be better than, let's see, do I have my desktop audio on? Oh, that's weird.
So we have another 5 minutes or so. Let's start thinking about closure under concatenation. So
I just want the picture. Okay, so basically what happens here is we got our two machines and we have some string for the input, and we're trying to say like, all right, for the concatenation language, we need to be able to break up our string into two parts. The first part gets accepted by the first machine and the second part gets accepted by the second machine. The reason why that doesn't work is because you might, if you eagerly jump to M2, like let's say just the way we construct it, if you hit an accept state at all in M1, then you instantly jump to M2 and then you start following its rules. You instantly jump to the start state of M2 with no consumption of an input symbol. So now you're at the start state of M2 and you just do the rest of it. It's not guaranteed that, even though there may be some place that you split X and Y, it may be that greedy option of instantly doing it the second that you hit an accept state is not actually the, like, you should have waited a little bit longer in M1 before you do the transition. So this leads into this really, really cool idea of non-determinism. So basically we're going to put a pin in trying to prove closure under concatenation. And we're going to move on to defining basically a new method of computation, a new way that we could compute that allows that allows branching and allows you to sort of split your computation into like alternate universes, into different paths. So okay, so this is an example of a non-deterministic finite automata. They call them NFAs. We'll just call them NFAs. And so look here, this is really cool. So this looks way different than a DFA, right? First off, here, there's no 1 coming out of here. In a deterministic finite automaton, for every state, we needed exactly the number of alphabet letters as outward pointing arrows. But here, first off, we have 2 1s coming out of Q1. So that means that there's 2 possible ways you could go. Then there's also no 1 coming out of here, but there's this weird thing called an epsilon, which is empty, meaning you could take it without consuming an input. Okay, the accept state and the start state are the same. Okay, so state Q1 has 1 exiting arrow for 0, but it has 2 for 1, for the symbol 1. Q2 has 1 arrow for 0, but none for 1. So in an NFA, a state may have 0, 1, or many exiting arrows for each alphabet symbol. Okay, and what this comes down to, if you know data structures, before I jump into that, let's just read this paragraph, because this is an important paragraph. How does an NFA compute? Suppose that we are running an NFA on an input string and we come to a state with multiple ways to proceed. For example, say that we're in Q1 and the next input symbol is a 1. After reading that symbol, the machine splits into multiple copies of itself and follows all the possibilities in parallel. Each copy of the machine takes one of the possible ways to proceed and continues as before. If there are subsequent choices, the machine splits again. So you just keep splitting, and then, this is important. If the next input symbol doesn't appear on any of the arrows, the outward pointing arrows, then that branch of the computation just dies out, and you just don't continue it. Okay. Finally, if any one of the machines or sort of branches of computation is in an accept state at the end, then the whole NFA accepts. So you just need one path. You don't need like all of them. You just need one path to hit the end at the right time. Okay, if a state with an epsilon symbol on an exiting arrow is encountered, something similar happens. Without reading any input, the machine splits into multiple copies of itself, one following each of the exiting epsilon labeled arrows and one staying at the current state. So you sort of get all the combinations of the epsilons. Okay, this picture is the best picture. So deterministic, there's really only one way to go. Here you have multiple ways to go. And if any accept, then the whole thing's accept. This is another way to look at it. This is a run of a real computation on this machine. They do this thing. They say, keep your fingers on it to keep track of which computations you need to do. This is the better way to state it. Well, when we get to the formal definition, I'll show why you don't need to do this finger thing. The punchline is that in comparison to a DFA, where the type signature of the transition function was the Cartesian product was a pair of state and alphabet, now you're going to a state. Now you're going to get state, alphabet to a subset of states. So you have a number of possibilities. So the A of the language consisting of all strings over 0, 1 containing 1 in the third position. Now, it's just another example. This is the smallest DFA that, okay, so We haven't done the proof yet, but every NFA can be converted into an equivalent DFA. We're going to do that in like a minute here. Oh, this is a cool one. If you're watching, not that anyone really would, but this is a very cool example. So you don't need, you can just have one symbol in your alphabet, and this actually computes something non-trivial. Basically, it's only going to accept if the number of if the input string is of length either 2n or 3n. So basically, if we start here and it's empty, then we accept. Now we go one more, now we're over here. Then we go one more, we're here and we're here. So we're still accepting all these. The only thing is that if we have one, so if we go if we're here and here, then we don't accept. And if we're here and here, we do accept. Then if we're here and here, we do accept. But then we get to here and here and we accept, and finally here and here we don't accept. So basically what I'm saying is that, the empty string 2, 3, 4, and 6 accept, but 1 and 5 don't accept. So you need to be a multiple of 2 or 3. So unary NFAs can actually compute non-trivial stuff. So this is a cool example in my opinion. Because you might think, like, what the hell can a unary alphabet do? But it actually can do some cool stuff. Let's see, what do they say? This is just another example. All right, we'll do another example just to like drill it down. So we're gonna see what can it do on the empty string. It accepts the empty string. So if we look at what the transition function does on the empty string, the possible states that we're going to be in is 1 and 3. Since that set contains an accept state, we are going to accept. A accepts for an interesting reason. So we start at our start state and we take our epsilon down to Q3, right? Then we go to A and we arrive back at our accept state. So A accepts as well. Now let's just take BA. This one is another example where BA, and then we die. There's no way to go out from here from B. So that branch of the computation fails. But now let's try B, A, B, A, and we accept. And then B, A also accepts. So that's that last one. And then just B goes to here, and then it can't go anywhere else, so it dies. And then B also dies because there's no epsilon going over to Q1 from Q3. And then BA, B die, BA die. Okay, so there's no way for any of these to accept. Oh, here's the formal definition. This is what I wanted to get to because this is the important part. The type of the transition function is now the codomain of the transition function is now a power set of the states. Also, the start state. Wait, hold on. Oh, and the other thing that's changed is this sigma epsilon. The alphabet is now written as the original alphabet union the epsilon symbol. So we now produce a set of possible next states. So this is the big change of the whole thing between NFAs and DFAs. I thought there was one more thing, though. The formal definition in an NFA is similar to that of a DFA. Both have states, input, alphabet, transition function, start state, and collection of accept states. However, they differ in one exception. Yeah, this is the main thing. It's just the type of the transition function. In a DFA, the transition function returns a single state. This returns a set of possible next states. Okay, if you don't know what power set is, go look up power set. It's and understand what the cardinality of the power set is, because it's going to be 2 to the n. Okay. So here's what one of these looks like. Here's our transition function. See here, instead of having a single symbol in here, we're going to get a set of symbols. Okay, and then this is the definition of what it means to compute or what it means to accept for an NFA. And the important part is yeah, so before we said Ri plus 1 is equal to the, but it just has to be an element of it. Because this is just updating the type of the transition function from being a single state to being a power set of the states, or an element of the power set, so a subset. Oh, this is great. This is the coolest. I really like this. The conversion of a NFA to a DFA. This is badass, man. So what you do is, if you recognize that, okay, let's say I have a set ABC, and I want to construct all subsets of that set. Well, I'm going to have 2 choices for whether or not to include A. I'm going to have 2 choices for whether or not to include B, and I'm going to have 2 choices of whether or not to include C. See if we get a picture. Wow, why are all these pictures terrible? Anyways, that's going to be 2 to the n. So what we're going to do... Oh, man. They keep going into my eye, dude. Why do they keep going into my eye? Okay. So here's what we're going to do. The way... And actually, this is like very similar to the Cartesian product construction that we did just a minute ago. The only thing is that we have way more branches to keep track of. And so the way we're going to do that is that we are going to make the set of states not the Cartesian product, but the power set. Where's a good picture? Yes. So, okay. So here is... Okay. So we're going to be converting this NFA into a DFA. And so since we have 3 states, we're going to have 8, 2 times 2 times 2 states in the DFA. Let's just go back to this proof. Do we need to go through this proof? I kind of want to let it land on my eye, but I really don't. Okay, so here we go. Let's just go through the construction. So the new set of states, Q is almost always the set of states in these things. So is the power set. Then we define the transition function to be oh, and I guess the important part is that in this we start with no epsilon arrows, but later they just define this epsilon closure where, like, after you move, then you add in the epsilon arrow stuff. But basically it's just going to be the union of... Okay, let's say we're at some point in our computation of our NFA. That means that we're in a set of possible states, or we're in a set of states. Then what our DFA is going to do is, for each of those states, it's going to call the transition function, and it's going to take a union, or actually, what our NFA is going to do is call the transition function of the NFA on each of those states and take the union. And that's going to be equal to the next set of states that we transition to. This is going to end up being a single state in the end. This is going to end up being a single state once we convert it to a DFA. Because each subset of states is going to have its own state. Okay, that's pretty basic, pretty obvious. And then remember, this is with no epsilon arrows. So for our start state, it's just going to be the singleton set of the original start state. That's all chill. Now this is really cool. Okay, I like this. So remember, the DFA's states is going to be the power set of states of the NFA. Now, in that power set, for each set in the power set, we check whether or not that set includes an accept state. If it includes an accept state, then that set in the DFA is an accept state. So it kind of broadens out in a way. Okay, now we need to consider the epsilon arrows. So we define this function E of R. I think sometimes it's called the epsilon closure, but basically, it's going to be the collection of states that can be reached from members of R by going along epsilon arrows, going only along epsilon arrows. So this is the formal definition. The epsilon closure of R, which is a set of states, is the set Q such that Q can be reached from R by traveling along 0 or more epsilon arrows. So you can do 2 epsilon jumps and it's still good. Okay, now we just take our original transition, or our new transition function, and we modify it so that after we call the transition function, we then take the epsilon closure of it. Not that hard. We also need to modify the start state so that the start state is also the epsilon closure of the start state, the original start state. So this becomes this. All right. This corollary is kind of boring, but it is used in the book and in the exercises. So understanding that a language is regular if and only if some NFA recognize it. Well, we just proved that an NFA is a DFA, and by definition, a language is regular if a DFA recognizes it. So we're all good there. Okay, so yeah. All right, we should look through this, but I don't know how I'm going to do this with... We're just going to have to jump up and down a lot. So, all right, so let's start by looking at this thing and figuring out what we need to do. Remember, these 8 states are going to be the states of our new machine. That's why this thing has 8 states. Okay. So first, let's figure out the start and accept states. So the start state is going to be E. So we have one accept state in the NFA. We're going to now take the epsilon closure of that. So we need to go along 0 or more epsilon transitions. So 1 is obviously in the start state. 3 is also in a start state because we can follow this epsilon. So therefore, the set 1, 3 is going to be the start state of our DFA. So you can see here, 1, 3 is our start state. So see this arrow coming from nowhere? That signifies that it's a start state. Okay, now we're going to figure out what the accept states are. So because 1 is an accept state, and it's the only accept state, then any subset of this, any element of this set that contains a 1 is also going to be an accept state because it represents the NFA's branches of computation being in these states. And we only need 1. So therefore, these 4 are the accept states. All right, now the transition function is very fun. This is something that, honestly, you can't really watch a video, like even me, and understand this. Like, I think you probably have to do it yourself to, like, get a little bit of intuition for doing this. But anyways, let's So this is D's states. So when they say D's states, that's what it is. It's those. It's the power set. So each of D's states goes to one place on input A and one place on input B. We illustrate the process of determining the placement of D's transition arrows with a few examples. All right, so in state 2, let's say we get an A, and we're in 2, and that's the only place we're at in our NFA. And someone hands us an A. Well, we have 2 places we can go, so we're going to branch out. So we can either go to 2 or we can go to 3. Therefore, the definition of delta on the set 2A is going to be equal to the set 2, 3. Oh, and yeah, and check. There's no epsilon arrows. State 2 goes to 3 on B and nowhere else. So it's just going to be 3. All right, you continue on doing that. I don't remember if there's any other surprising things, but we're going to do them in worked examples. So, anyways, this is the final result. This is a DFA that's exactly identical, recognizes the same language. It's equivalent to this NFA. I don't know if I'm going to be able to get to the exercises. I have an hour and a half left, and we have to cover a lot. So I might rename this just to be non-determinate or finite automata, basically. Okay, so now that we've covered, this is just saying, that you can simplify this state with 8. But and one thing I wanted to show, if you look up the Rust regex library, and you look up exponential. There's something in this documentation that explains that the let's look up. Oh, there we go. I don't know where it says it. I remember it says it somewhere. But anyways, the idea is that since we're doing this power set construction, you can get an exponential blow up in the size of the corresponding DFA. Okay. So now that we've explained non-determinism and we've proven that our model of non-deterministic finite automaton is actually the same as deterministic finite automata, it's just easier. We're going to revisit the proofs of closure closure on the regular operations. So they actually do union first. Even though we already did union, they're like, look, union's so easy now. All you have to do is you take 2 NFAs, which are both equivalent to DFAs, and you just put them together with the new start state, and you add epsilon arrows to the original start states. And now they're going to proceed as before, and if either of them ended in an accept state, then we accept. So clearly union does exactly what we want it to. And you could go in and try to like convert this to a DFA, and you would see, your power set gets really, really big, but no matter what, you're still going to, if either of them end in accept, then you're good. Now, this is the formal proof. Here, generally in these proofs, what you need to look at is like most of this is stitched together. You see you get the extra start state here, and you make it the start state, but the transition function is usually the most important part. So you see here, the transition function is just defined by stitching them together. And then if you're in the start state and you have an epsilon, then you go to the start states of the things you're taking union of. So that the N1 and N2, you just go to here and here. And then the empty set, basically, if let's say that you decided to just stick around at this start state, anything else dies. So that's just the formal way of saying that. So you sort of have to take those epsilon transitions in order to not die. Okay, concat is cool, and I love these pictures. Concat is what you do is this allows you to basically non-deterministically jump to the next one and find. I guess one of the things to say about NFAs is like, yeah, it works, but if you really are thinking about state size, I'm sure that people have looked into like what can be computed for a given scaling of the number of states. Because sure, you could have like a bajillion states, but like it might take more memory than you have. Anyways, for a concat operation, all you do is you take the accept states of your first. So here's what we're trying to do. We are trying to compute A1, which is a language, concatenated with A2. So all the strings in A1 with all the strings in A2 after it. All we do is we take the accept states of N1 and we add epsilon, we remove them as accept states, and we add epsilon transitions to the start state of N2. So, all right, same states as before. Start state is the first start state of N1, or the start state of the concatenation is the start state of N1. The accept states of F2 are just the accept states of N2. And then here's the transition function. So if Q is in Q1, which is in the first NFA, and it's not an accept state, then just proceed as usual. If it is in an accept state and it's not epsilon, proceed as before. Now, if it is an accept state, and it's an epsilon arrow, then what you're going to do is you're going to say, you can go to all of the epsilon transitions that you had before, and you can also go to the start state of the second NFA. And that's just adding a single arrow. So honestly, this notation is more complicated than just this picture. But anyways, and then finally, if you're in N2, just like proceed as before. Okay, star. I really like star. Star is cool. I always forget star. But basically, if you're trying to show the closure of the star operation, this is what you do. You add a new state, and it's an accept state. And we know that because for any language, a star means 0 or more. So the empty string is always an accept state of something star. So what we're going to do is we're going to add this accept state. And I think they say that there's an exercise that says yeah, there's an exercise that shows how this fails, but I mean it's like so obvious. Like there could be arrows that point to this start state. So you would get unwanted strings in your language if you didn't do this, cuz in this construction there's no way to get back to this empty guy. So this is always going to be the empty state. Anyways, so then now that we've handled the empty string appropriately by adding a new state, we're going to add an epsilon transition to the original start state. Then finally, we're going to proceed as before, but we're also going to add epsilon transitions to from the accept states of the NFA to the start state of it, to the original start state of it. So that means that you could start looping this thing around and around. And I think technically, maybe not, I don't know. I think technically you could have made these epsilons go to here and you would just take 2 hops, but I think it's equivalent. I just, I don't know. All right, we don't need to look at this. This transition function is like pretty obvious. All right, now we're getting on to 1.3. 1.3 is a pretty sweet section, and I kind of want to go over it a little bit slower. Okay, so they say, oh, there's this stuff called regular expressions, and they're used in all over the place. Okay, this is what I'll say. We can use the regular operations that we just defined and proved all the closure stuff for to build up expressions that describe languages. These expressions are called regular expressions because they represent regular languages. Here's an example. This is an example of a regular expression, and it's basically saying it's the language that starts with a 0 or 1 and then ends with 0 or more zeros. Um, 0 and 1 are shorthand for the sets 0 and 1. So the value of this expression is the set 0, 1. This is just saying, like, I mean, it's good that they spell this out because otherwise there'd be a little bit of abuse in notation. But once you spell out that we're talking about sets and it's all operations on sets and languages are just sets, then it becomes a little clearer. Okay, concat is implicit. So if you see something next to each other, like, oh, like here, there would be a concat, there'd be a circle in there between the parentheses and the 0, but it's, you don't really need it. Oh, yeah. This is actually shorthand. And I think they said precedence rule somewhere. The precedence is star, then concat, and then union. Unless parentheses change the order. Okay, so we're just getting more examples. Now this one would actually be everything. So if your alphabet was 0 and 1, then this would be any possible string. Okay, that's chill. Okay, this is cool. This is a good definition. I like this definition. Hold on, I'm gonna get some water. Okay. Okay, so the cool thing here is that a regular expression is this inductive type. So it basically, there's a few base cases. You can either have a letter, you can have the empty string, or you can have the empty set. And then the inductive parts of this, the non-base case, is the union of any two of these, or really any of this. So the regular operations on the whatever. This is like so obvious, right? You have two regular expressions. Their union is also a regular expression. Then also you have two regular expressions. Then their concatenation is also regular. And then finally, if you have a regular expression R1, then R1 star is also a regular expression. And so you can build up bigger and bigger regular expressions from these. In items 1 and 2, the regular expressions A and epsilon represent the languages. Get out of here, man. Represent the singletons. The way that I like to think of this epsilon is I like to think of it as just like a double thing. Like this is what epsilon is. Whereas if we were to have like this, oh yeah, so don't confuse epsilon and the null set. Precedence, inductive definition. You're guaranteed that to always hit a base case because we require that you can't make a circular definition basically. So that's chill. I mean, anybody that's programmed before you, that's fine. I mean, a tree, it's a tree. Oh, okay. We should walk through some of these examples. These examples are cool. The language that contains a single one, 0 star 1, 0 star. That's cool. Has at least 1 1. That's cool. Sigma star 1, sigma star. So you could so the string just 1 by itself is an element of this language. What else? This is like a subsequence one. So if it has 001 as a substring, did they define plus? Oh, here we go. For convenience, we let plus be R star, meaning 1 or more, as opposed to 0 or more. Oh, and by the way, for anybody that's curious, I think like PCRE is not actually like the set of languages that Perl regular expressions can recognize is actually not regular. Because it can do like backtracking and all this crazy stuff. And look ahead and all this crazy stuff. None of that is legit, man. That's all hacks. That's all hacks. That's nothing, man. It's a superset. It can recognize more languages. Let's look at their GitHub. Kind of wild. It has 1,000 stars. People are still writing it, though. All right, anyways. Enough of this applied nonsense. right, so you get the idea, though. This one's cool. Even length. Every 0 is followed by at least 1. That's cool. Anyway, so you can see here how you can build up cool expressions and languages from regular expressions. Oh, this is a good digression. So if you were, so R is a regular expression. If we take the union of the empty set, we're just going to get R. Similarly, if you take R and you concatenate the epsilon string onto it, it's still just going to be R. But if you switch them around, then the union of the R and the empty string may not be equal to R because you might add in a string. So like, let's say R is just equal to the character 0. Then the language is just the set 0. But then this, the union with the epsilon string, you get epsilon. You get an empty string, which again, I like to think of as just double quotes. Oops. All right. And this one goes downward. Concatenating with the empty string is it just kills everything because there's no element of the empty string, or sorry, I had to be more precise. There's no element of the empty set. The empty string actually is a non-empty set. Okay, here's an example of like number parsing. This is a regular expression for parsing numbers. And then they say, look, there's applications to it. Okay, now here's where we get to some good stuff. We're going to show the equivalence that regular expressions and finite automata are actually the same in their ability to describe languages. So they have certain capabilities, descriptive power, and it's the same. It's kind of amazing, right? It's like you don't really think of them being the same, but they are. And we're going to walk through how you do that. Okay, so theorem. A language is regular if and only if some regular expression describes it. So it's two directions. So we assume a language is regular, and then we prove that there's a regular expression that describes it. And then we go the other way. Assume we have some regular expression, show that it's regular. So what I think happens is that if you assume it's regular and then you show a regular expression, you're going to take a DFA and convert it to a regex. And then you're going to go take a regex and convert it to a DFA. And when you do that, then you've shown that they're the same. So we start with the first lemma, which is a language is described by a regular expression, then it's regular. Oh, this is a good proof. I'm going to walk through this proof kind of slowly. I don't think we're going to get as far as I wanted today. I really wanted to do the exercise, but you got to get through this. Okay. All right, so the proof idea is, say that we have a regular expression R describing some language A. Oh, okay, we go the other way. Okay, this is starting the other way. We show how to convert the regular expression R into an NFA. And the way that we do that is we're going to take those 6 base cases And we're just going to show how to make an NFA for each of them. And that will give us an inductive way to build up from any regular expression the corresponding NFA. And we'll do a couple practice problems on that. All right. So for the first case, if R is just some letter, then the language is just some letter too. So then we just make the most basic language is just a language that on the single symbol accepts. Okay, that's the formal definition of the NFA that okay, for 2, so this is where R is just equal to epsilon. This first one is where R is equal to A. So we just get a single state that accepts. For the third case in the definition, we just get a this is R is equal to the empty set, and it's a single state, but it rejects. So see how there's no double circle? It rejects this. Oh, and then these, we already proved, when we proved the closure, wait, all right, this example I've worked through a number of times and I still sometimes get it wrong. ABUA star. Okay, so first off, so how do we handle this? All right, so we're going to build A and we're going to build B. So this is A. This is the regex A. And the regex B is equal to the same thing, just with a B instead. Okay. All right, so then AB is equal to A at, before B. Yeah, so what we do is we take A, and then we add an epsilon transition between its accept state and the start state of B. So this is R is equal to A after B. Okay. All right, so now we're going to do A, B, U, A. So then the union rules, if we go back, let's duplicate this tab. The union rules were in here. So what we're going to do is we're going to add a new state, and then we're going to add an epsilon arrow to both of them. Yeah. So we're going to add an epsilon. So we're going to get A, B. This is going to be this, A, epsilon, B, except. Then here it's going to be epsilon, A, except. Okay. Yep, that's exactly what I got. And now A, B, U, A, star. So for star, we add a new state that's an except state. Then we add an epsilon transition to this old start. Then we copy what we had. And then you add an epsilon transition to the old start. Cool. All right. That's how you make the NFA from regex. So that's the first half of the proof. Now we just have to go the other way. So they do another example. That's pretty cool. We're not going to do another example, but that's fine. Okay, so now the other way, lemma 1.60. If a language is regular, then it is described by a regular expression. We need to show that if a language A is regular, a regular expression describes it. Because A is regular, it is accepted by a DFA. We describe a procedure of converting DFA to regex. Okay, so this is a DFA to regex. All right, how do we do it? We break this procedure into two parts using a new type of finite automaton called a generalized NFA, or a GNFA. We show how to convert DFAs into GNFAs and then GNFAs into regular expressions. The generalized non-deterministic finite automata are not simply non-deterministic finite automata wherein the transition arrows can... GNFAs are simply NFAs where the transition arrows may have regular expressions as labels instead of just members of the alphabet or epsilon. The GNFA reads blocks of symbols from the input, not necessarily just one symbol at a time as an ordinary NFA. All right, so here's an example of a GNFA. See the arrows? They have full regex on them. So I think like if you're coming from here, yeah. You could either take you could take two A's out of it, or you could. I don't even know how you convert a GNFA into an NFA, man. I think you don't really need to though. I think there's no, or actually no. I know how to do it. You would just you would undo the process that we just did. I mean, you would just start to add new states. All right, we require GNFAs that the start state has transition arrows going to every other state and no incoming arrows. And the accept state, there's only a single accept state and it has arrows coming from every other state but no arrows going to any other state. And the accept state and the start state have to be distinct. Okay. And then all non-start or stop are fully connected, including themselves. So they have a self loop. Okay. We can easily convert a DFA into a GNFA in the special form. We add a new start state with an epsilon arrow to the old start state and a new accept state with an epsilon arrows from the old start accept states. If any arrows have multiple labels, or if there are multiple arrows going between the same two states in the same direction, we replace each with a single arrow whose label is the union of the previous labels. Okay. Oh, and we add, okay. Oh, that's how we do it. All right, that makes sense. You add a empty set arrows. Okay, now it's time for the conversion. I wish they had an example of the conversion on this first step. We definitely need to do this because I don't. The way we do it is we go. I want to know this step for sure. Now we show how to convert a GNFA into a regular expression. Because a GNFA must have a start and accept state and they must be different from each other, we know K is greater than or equal to 2. If K is greater than 2, we construct an equivalent DNFA with K minus 1 states. This step can be repeated until the new GNFA can be repeated on the new GNFA until it is reduced to 2 states. If k is equal to 2, the GNFA has a single arrow that goes from the start to this except, and the label of this arrow is the equivalent regex. That's so cool. That's so cool. All right, so yeah, so the inductive step is the important part. We need to select a state and then rip it out of the machine and repair it. Repair the rest of it so that it's still the same language. Any state that's not start or except will do. Such a state is guaranteed to exist because k is greater than 2. After removing qrip, which is the ripped out state, we repair the machine by altering the regular expressions that label each of the remaining arrows. The new labels compensate for the absence of it by adding back the lost computations. The new label going from state qi to qj is a regular expression that describes all strings that would take the machine from qi to qj either directly or indirectly through qrip. All right, so this is a great picture. This is probably one of the best pictures in the book or in this first chapter because it's just so smart. It's like, what a great way to do things. So I to j, this thing is going to have on it, it's going to be R1, R2 star, R3, union R4. Did I get that right? Yeah. R1, R2, star, R3, union R4. So that's all you have to do, really. QI goes to QRIP with arrow labeled R1. In the old machine, in the new machine, yeah, okay. The formal proof. I don't remember liking this proof. Actually, wait, hold on. And then you recurse. Okay, this code is not too hard to understand. I don't know. I feel like it obviously works. All right, so yeah, so let's convert this into a regex. Okay, so what do we do first? Step 1, make 4-state GNFA with new start and accept. Okay, then we also change the AB into AUB. Okay, then we remove state 2. So first let's draw the 4-state one. So we have S with an epsilon to 1. This is an A. Then we have 2, and this is a B, and then this is an AUB. And then this finally is an epsilon with an A. Now we let Q2 equal Q rip. So we're going to rip out 2. Okay, so what is that transition going to be? It's going to be so if this is the empty string is from 1 to A, this is going to be R1. We have R1 union B A U B star epsilon. So what does that become? B A U B star, and then the epsilon just becomes nothing. Okay. So this is going to be reduced down to okay, so now we're going to redraw that. We're going to get S to epsilon to A to A, and this is B A U B star. Now finally, 1 is the Q rip. So then we're going to get empty union epsilon A star B A U B star, which is equal to A star B A U B star. A star B A. Yeah, cool. So then this is the final regex. This is a good example. Doing a 3-state one, bro. I remember doing this example, and it was just like No freaking way. This thing goes off the page, man. All right. All right, let's pack it up there. We'll do non-determinism, non-regular languages, and the exercises later. The non-regular languages is actually the coolest part of this, because it starts to give you a sense of what the power is, like how powerful are regular languages. Pretty powerful, actually. They can do a lot of stuff. And one thing to note: any finite language is regular. What's the proof? I don't know. I think you just build a really big DFA that recognizes each one individually. But what if you like don't know what the elements of the language are? How do you construct it if you don't have an explicit way of generating all? You must though. If it's finite, then you must. All right, whatever. Yeah, you just build a big NFA. Yeah, this is what I was thinking. You just do this. You take this regex and then you make the um the NFA for it? You make the NFA for it. Okay. So that's